Hi, this is your video for sections 5.1 and 5.2, and this is the beginning of chapter 5, which is all about probability. So section 5.1 is about some basic probability rules. The objectives in this section are 1. Define basic terms and notation. 2. Apply basic properties of probabilities. 3. Compute and interpret probabilities using the classical method. 4. Compute and interpret probabilities using the empirical method. And 5. Use the law of large numbers. Objective 1 is to define basic terms and notation. So, probability is a measure of the likelihood of an event occurring. In probability, an experiment is any process that can be repeated, with results that are well defined and measurable. The sample space, S, of a probability experiment is the collection of all possible outcomes or results of the experiment. And an event is any collection of possible outcomes or results from a probability experiment. An event may consist of one outcome or more than one outcome. Those with only one outcome are called simple events. In general, events are denoted using capital letters such as E. Here's some examples of probability experiments. First, we have the experiment of tossing a coin. Now, the possible outcomes of tossing a coin are heads and tails, so our sample space would be the set of those two outcomes, heads, tails. Our next experiment is rolling a die. We assume this is a normal die with 6 faces. So the sample space would be all of the whole numbers from 1 through 6. Another type of probability experiment we could conduct would be to select a part and inspect it. So the results of the inspection could be either that the part is defective or that it's not defective. So that would be our sample space. Another experiment would be drawing a playing card from a deck and recording just the suit. So we would have 4 possibilities for the suit, and that would give us our sample space: hearts, diamonds, clubs, and spades. Now, in that last experiment of drawing a playing card, we could define an event R as drawing a red card. Now, since there are 2 of these suits that include red cards, our possible outcomes for the event would be hearts and diamonds. So we could also define R as a set and just include the 2 outcomes that would be possible in that event, which would be hearts and diamonds. Now, R is not a simple event because it includes 2 outcomes instead of just 1. Another type of experiment we conduct frequently in this course is conducting a survey. This survey asks 2 questions: the respondent's gender, male or female, and his or her age category, either under 18, 18 through 65, or over 65. So the sample space would be the set of all possible responses to the 2 questions. So we have to look at how the respondent answered both of the questions. So here are the possibilities. They could have either answered that they were male and under 18, male and 18 to 65, or male and over 65, or they could have answered that they were female and under 18, female and 18 through 65, or female and over 65. Now, in this experiment, we could define an event O as a respondent's age category being over 65. There would be 2 possible outcomes for this event from our sample space. That would be either that the respondent is male and over 65, which would be this one, or that the respondent is female and over 65. So we could define our event O in set notation as those 2 outcomes: male and over 65 or female and over 65. In the notation for probabilities, we use capital P to stand for a probability. We use other capital letters A, B, E, F, and so on to denote specific events. And capital P of A denotes the probability of event A occurring. So that was the same as saying the probability of A. The upside down U stands for an intersection. So if we say A intersection B, we're looking at the intersection of events A and B. In other words, where both A and B are occurring at the same time. Now when we use a U, that's A union B, and that means that either A or B or both are occurring. Objective 2 in this section is to apply basic properties of probabilities. So probabilities can be given in decimal form or as percentages. Actually, they can also be given as fractions. A probability cannot be negative. It also cannot be greater than 1 or 100% if we have it in percent form. The sum of all the probabilities for all the outcomes in a sample space has to be 1. And an unusual event is one that has a small probability of occurring. And typically this is less than 0.05 or 5%. Now the range of values we can have for probabilities, again it goes from 0 at the bottom up to 1 at the top. An event with a probability of 0 means that the event is impossible, that there is no way that it can happen. Whereas an event with a probability of 1 means that that event is certain to happen. This would be the case when your event includes all of the outcomes in the sample space. And there's a whole range of values in between. For example, 0.5 or 50% means that there's a 50-50 chance that the event will happen, and so on. Now in this section we're going to talk about a probability distribution, and here we're just talking about a probability distribution as a table that lists the possible outcomes of a probability experiment and each outcome's probability. We'll get a little bit more specific about probability distributions in the next chapter. So the probabilities in our distribution table can be given as fractions, decimals, or percentages. Again, the probabilities have to be between 0 and 1. It could be either 0 or 1. Or if we're doing it in percentages, they could be between 0% and 100%. And the probabilities in the table have to add up to 1 as long as the table includes all of the possible outcomes that are in the sample space. Here's an example. A survey conducted in a certain state asked respondents their gender, male or female, and their age category. Based on census data from this state, the percentages of the state population in the 6 different categories are these in this table. So we can use this information to list the probabilities of a randomly selected state resident answering the gender and age questions in each of the 6 possible ways. So here are our 6 possible outcomes, and here are the probabilities, and we just got those from the percentages over here. In this case, they're just written in decimal form instead of percentage form. Objective 3 in this section is to compute and interpret probabilities using the classical method. So an experiment is said to have equally likely outcomes when each simple event has the same probability of occurring. And the classical method of computing probabilities requires that we have equally likely outcomes. So the way we do this is we assume that a probability experiment has n equally likely outcomes, so that each simple event or each outcome in our sample space has the same chance of happening. Now, if the number of ways that event A can occur is S, then the probability of event A is S over n. In other words, it's the number of ways A can occur, or the number of possible outcomes for event A, divided by the number of events, the number of outcomes in the sample space, or the number of total possible outcomes for the experiment. Here's an example. A die is rolled and the number on the face is recorded. If the die is fair, so that each of the 6 faces is equally likely to come up, what is the probability of rolling a 2? What is the probability of rolling a number less than 5? So first, let's look at our sample space. The possible outcomes for this experiment are the 6 faces on the die. So our sample space is the numbers 1 through 6. Now, the event of rolling a 2 can only happen in one way. The event has only one possible outcome. So the number of ways the event can happen is 1. The number of outcomes in our sample space is 6. So the probability of our event is 1 divided by 6. Now, to find the probability of rolling a number less than 5, first we have to determine the number of ways in which that event can occur. Or another way to think about it is the number of possible outcomes for that event. So if the number has to be less than 5, that would mean it could be a 1, a 2, a 3, or a 4. That means there are 4 different ways that our event can occur. So our probability is 4 divided by 6. Again, we're taking the number of ways that our event can occur, or the number of outcomes in the event, divided by the number of outcomes in our sample space. And here we end up with a fraction 4 over 6, which we can reduce to 2/3. Here's another example. The students in a high school history class include 7 female juniors, 3 male juniors, 9 female seniors, and 11 male seniors. A probability experiment consists of selecting one of the students at random. What is the probability that the student is a male junior? What is the probability that the student is a senior? Well, first of all, our sample space consists of all 30 students in the class. And I got the 30 just by adding up all the different categories of students and how many there were. So 7 plus 3 plus 9 plus 11. Each different student represents one simple event in our sample space. If our student is randomly selected, then each student is equally likely to be selected, so each outcome is equally likely. Now, the event of selecting a male junior can happen in 3 ways because there were 3 male juniors in the class. So it could be any one of those 3 boys. That means the probability of this event is 3 divided by 30, which was the number of outcomes in our sample space. So that's the same as 0.1 or 10%. The event of selecting a senior can happen in 20 different ways because there are 9 female seniors and 11 male seniors. That gives us a total of 20 seniors in the class. So the probability of selecting a senior is 20 divided by 30, and we can put this in a fraction form or we can write it in decimal form, and here I rounded it to 4 decimal places for 0.6667.
Objective 4 is to compute and interpret probabilities using the empirical method. So the empirical method is also called the relative frequency approximation method. In this method, the results from many repetitions of a probability experiment are used to calculate the relative frequencies of the different outcomes. The relative frequencies are then used to approximate probabilities for future repetitions of the experiment. So to compute the probabilities, we assume that a probability experiment has been repeated n times. Each repetition is called a trial. The probability of an event A is approximated by the number of times event A occurred, divided by the number of trials of the experiment. So we're just computing the relative frequency of event A in the n trials. Then to approximate the probability of A, we take the number of times A occurred, or the frequency of A, divided by the number of times the experiment was repeated, or the number of trials. Here's an example. Pass the Pigs is a game in which pigs are used as dice. Points are earned based on the way the pig lands. There are 6 possible outcomes when one pig is tossed. So a class of 52 students rolled pigs 3,939 times. The number of times each outcome occurred is recorded in this frequency table. So our problems are A, use these results and the empirical method to create a probability distribution table. B, estimate the probability that a thrown pig lands on the side with dot. And C, estimate the probability of throwing a leaning jowler. So first, we're going to divide each frequency by 3,939 to get the relative frequencies. And these are our approximate probabilities. So here are our relative frequencies. We just took each one of those values in the frequency table and divided by 3,939. So now we have our probabilities approximated by those relative frequencies. So now we can calculate the approximate probability that a thrown pig lands on the side with dot. So that's just 0.329 or 32.9%. The approximate probability of throwing a leaning jowler is 0.008 or 0.8%. And since this is less than 5%, that would mean that throwing a leaning jowler qualifies as an unusual event. Here's another example. Survey results are often used to approximate probabilities using this empirical method. So we have a recent Gallup poll of 1,020 adults in the United States that found that 42% of those surveyed approved of the way the president was handling foreign policy. 51% did not answer no opinion. Use these results to estimate the probability that a randomly selected adult in the United States approves of the way the president is handling foreign policy. So using the empirical method, an estimate of the probability that a randomly selected U.S. adult approves of the president's handling of foreign policy would be 42% or 0.42. Again, we're using results from past trials of the experiment. In this case, the experiment would be selecting one adult and asking them the question in the survey. So this poll would have had 1,020 trials of that experiment, and we're using the results from those 1,020 trials to predict what would happen if we randomly selected another individual with those same characteristics of being a United States adult and asked them the same question. And we're using this to predict what their response would be. Objective 5 in this section is use the law of large numbers. The law of large numbers states that as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the classical probability of the outcome. In other words, as a procedure is repeated again and again, the empirical probability, or the relative frequency probability, of an event tends to get closer to the classical probability. Here's an example. If we go back to the experiment of rolling a die, the classical probability of each one of the 6 outcomes is 1/6, or 0.1667, rounded to 4 decimal places. As we keep repeating this experiment, the relative frequencies of the outcomes should get closer to those classical probabilities. So let's say that we rolled a die 50 times. So we repeated the experiment with 50 trials. And we got these frequencies. Then our relative frequencies would be these. And notice that some of them are close to our classical probabilities, but most of them aren't all that close. Now, if we did the same thing only with 2,000 trials and recorded our results, and we got these results, notice that these are much closer to our classical probability of 0.1667. And the idea of the law of large numbers is that if we kept repeating trials, so maybe if we did 10,000 trials or 100,000 trials, these relative frequencies would keep getting closer to the 0.1667 as we did more and more trials.